Hello, I'm Mr. Franklin, and today we're going to be talking about friction. So, friction is an opposing force caused by the interaction between two surfaces. That is the overall description of friction. Now, as we get into it, what you're going to find out is friction can be very, very complicated. What else is new with physics, right? Um, so, one of the things we like to think about when we think about friction is this next point here, which is if we think of friction as a force that is opposite to motion because of the interaction between two surfaces, you'll have a pretty good idea of the basics behind friction. Now there's two general components of it, which we're going to get into in a second, but let's take a picture, take a look at what's going to be happening. So we have our box or book sitting on our table, and I'm going to push it with the force of 100 newtons. Now, we've all experienced this. We try to push something, and as we push it, we feel a resistance, like there's something that we have to overcome to get the box moving or the book moving. And that's what you're feeling there is friction, which we usually say capital F sub F, okay, force of friction. And it's because of, if we zoom in here, it's because of the type of surface. Now, like our smooth flat table probably is not, excuse me, our smooth flat table is probably not perfectly smooth, just like the box is not. And so we get an interaction between those surfaces as they slide across each other. So what force is it that, if we look here, what force is it that pushes these surfaces together? Anybody remember? So we have we're going to talk about the normal force, but right here we have the force of gravity pulling the book down. So but then we have the table pushing back on the book, and that's the normal force. So it's the force of gravity and the normal force that holds these two surfaces together as they slide across one another. Okay? So the book's weight, force of gravity, pushes on the table. The table pushes back on the book. And that's the normal force. Which law is this? Which of Newton's three laws is that? Okay? So it's Newton's third law, and then where does that force happen? It happens at the surface. Okay, so we're all interested in what's going on at the surface. So if I zoom in at our surface, we could, when we do this in our class, we are oversimplifying things when we just simply draw our normal force as a single point, because the book is not in contact at just that one point. We have a force of gravity acting, is felt all along this surface. Okay, same with the normal force. The resulting normal force is happening all along this surface. But if we add up all of those little bitty forces, okay, we would get a total force. If we add up all the forces of gravity for those little bitty points, we would get a total force. And so our approximation for what we're doing is good enough. The key important thing is this happens at the surface. So you change the surface, and you're going to change this thing that we're going to be talking about called the coefficient of friction. The coefficient of friction is an experimentally derived ratio that tells us how surfaces interact with each other. So what we've done as scientists is we've come up with a number that as we push, and friction happens, what type of surface gives us this number that we call the coefficient of friction, which we're going to talk about some more in just a second. But we're going to talk about this coefficient some more in just a second. So, but let's look at this. So we've got a force of friction. Got the force of friction. We have the force of gravity, and we have the normal force. Okay? Now, for the object to move, which one of these four forces, for the object to move to the, let's say to the right, which one of these four forces has to be greater than the others? Okay? Hopefully these two are equal. If they're equal, then the box will just slide on the table. It will not go up and down. It will not go up and down because we want it to go this way, right? So if we add these two forces, force push plus the force of friction, so 100 newtons, plus a negative 40 newtons, we get 60 newtons. Which direction? That way. Why? Because the force of the push is greater. Okay? Now, if the force of the push and the force of friction are equal to one another, then our resulting force is going to be zero. Now that could actually mean two things. If the force is zero, either the object is not moving or constant speed, right? It could still be moving, and if the forces are equal, it's just not going to slow down or speed up. Okay? All right. So let's talk about this force of friction before we actually show you this coefficient that I just drew on here. So the coefficient of friction is usually a number between 1 and 0. If it's 0, then there is no friction. If it is 1, then there is maximum friction. Coefficient of friction, we often use the Greek letter mu, pronounced with an M and the word U, mu, okay? And it's drawn like a letter U, but has a tail in front of it, okay? So sometimes I do my U and then I add the tail because I forget. And the tail is in front, not in back. Okay, the two components put together. So we've got our force of friction, we've got our coefficient of friction, and we've got our normal force. So if I know the coefficient of friction and I multiply it times the normal force, which is force normal is equal and opposite force of gravity, right? And the force of gravity is mass of the object times the acceleration due to gravity, right? So that's also the normal force. Okay? So mu times this normal force will give us our force of friction. Okay, now that's greatly simplified because there's actually two types of friction that we're going to talk about. There's static friction, which static means, what does it mean? Not moving. And kinetic, which means moving. So when we talk about kinetic energy later on, it's going to be the energy of motion. Kinetic friction. The objects are already moving. In static friction, the object is stationary. So static friction. I've got a guy here. He's trying to push a box. He's trying to push it this way. But the box is not moving when the box is stationary. He walks up, starts to push on it. So when he pushes, we have this force of friction. To make the box actually move, the force of the push has to be greater than the force of friction. So for example, if he pushes with 50 newtons, we don't want that. If he pushes with 50 newtons, and the force of friction is a negative 49 newtons in the opposite direction, we add up the total force, and we have a result of 1 newton. Result of 1 newton. Because it's positive, is the box going to move? Absolutely. Okay, so the box is now moving. But once he gets it started moving, now it's moving, we have kinetic friction. So it has some velocity, some positive velocity. He's still pushing on it with 50 newtons. But now what will often happen, it's not always true, is the force of friction will lower, because it takes a lot less, there's a lot less friction once something already has started moving. There's always exceptions, of course. But once we add these two together, we now have this force of 20 newtons. So some of you, if you're in football, you may have done this where you were trying to push the blocking sled. When you first hit it, you have to really give it a shove for it to get moving. But once you've got it moving, you actually don't need as much power. Okay, so you can actually back off the power. The same goes with the car. It might take you a little bit of push on the gas to get it started moving forward, but once it's moving, you can actually let off the accelerator. So let's take a look at this and apply it to our rocket model. So we have air going, we have our rocket, we have the launch pad, the force of gravity is pulling on the force of thrust, but what about friction? So we have air here in the orange, air going over our rocket. And air is made of particles including nitrogen, N2, oxygen, O2, water, H2O as a gas, and more. We can't see these particles, but they have mass and a surface. So if an object has mass, it has weight, force of gravity. So force of gravity, remember, is G times M1, M2 over R squared. Well, there's the mass of the Earth, mass of the air. There's going to be gravity between the two. We also simplify this on the Earth as mass times the acceleration due to gravity, right? So we can actually figure out what that weight is. It also has a surface. It can interact, and because of that, it can interact with our rocket. So if you don't believe me that air has mass, put your hand outside a moving car. The wind you feel is the air interacting with your hand. So here's the car, you put your hand out. You've got millions and millions of particles, and you can feel them on your hand. And basically as the particle moves over your hand, you got this particle moving over your hand, this is microscopic, you will get, it's moving this way, we get this force of friction in the opposite direction, and your hand feels that. Okay, the particle slides around your hand, and that's friction that you're feeling. So we take a look at our rocket, and we have these particles at the tip, and we zoom in even further, and basically we have the particle moving that way against the rocket, and we're going to get force of friction in the opposite direction. Now this friction right here, as it's drawn, is the friction on the particle. Okay, but because of Newton's third law, it's going to be equal to the force of friction on the rocket. But we have these millions of particles, so we have these millions of little frictions that if we add them up, we get a total force, and we get the force of friction on the particle, which is equal to the force of friction on the rocket, pushing down on the rocket. So, in the end, force of friction on the rocket is equal to the force of friction on the particle. But in our total diagram, because we're concerned about the rocket, we have the force of gravity, we have thrust, and then we have the force of friction. For our rocket to go up, the total force has to be equal to the force of the thrust plus the force of gravity plus the force of friction, and it has to be greater than 0 for the rocket to go up. And actually, it has to be significantly higher than 0 for the rocket to climb as high as we want it to go. So let's take a look at a car example. If we have a car on the road, as the tire spins this way, we have motion going this way. We have the force of friction on the tire going this way, opposite the direction of motion. Okay? But this force of friction is the friction of the, actually these are written backwards. Force of friction, this force of friction is the force of friction of the road on the tire. Okay? But that's equal to the force of friction of the tire on the road. Because they're different objects, the road doesn't move. The car is free to move, so the car actually moves forward. Okay? So the force of friction on the tire, the car moves. The force of friction on the road doesn't move. So when we look at, you step on the ground, okay, we're taking this example to the ground. When you're walking, you have your force of motion, you're going this way. You actually have a force of friction right here. That's your foot on the ground, but the reaction force is enough that it propels you forward. But when you step on ice, there's no reaction force, and so you have this force of friction going this way with no opposition, and so you actually slide because your foot is going this way because there's no pushback. Your foot slides. Zero pushback. Okay? So force of friction on the ground on me, the ground doesn't move, you do, but when there's ice, you have your force, you put your foot on the ice, and there's no pushback. So your foot slides. Those are simplifications. So now let's work a couple of practice problems. So following our steps, we have a sled which is pulled by gravity down a snowy slope with a parallel force of 80 newtons. So I circle it, put an F. A frictional force of 20 newtons, circle it, force of friction, opposes the sled's motion. If the sled and rider have a mass of 20 kilograms, or 80 kilograms, circle it, M, how much will the sled accelerate? A equals question mark. Okay. Then I actually already drew the picture, but I've got my sled here, okay, and my rider, stick figure rider, and then have my friction force in red of 20 newtons, and the force of the slide, which is 80 newtons, and my mass of 80 kilograms. Now it says a parallel force. What they're talking about here is the slope is this way, and the force is parallel. If it wasn't parallel, then we would have to do all kinds of angle work because the force of gravity actually pulls literally straight down, and the normal force is at an angle. We would have a bunch of other calculations we would have to do. But they've already done those calculations for you. The force of friction is parallel to the surface, which means the surface is this way. The force is in the same direction as the surface. Okay? Anyway, so now we're going to do our KUF chart. So our knowns, I've got a force of friction equal to negative 20 because it's going in the negative direction. The force of the slide, which is 80 newtons, and a mass of 80 kilograms. My unknowns is acceleration, but in order to find acceleration, I've got to know the total force. So that's my other unknown. Because I got two forces, I'm going to have to find out what the total of those two forces is, which the equation from your equation is. Force total is F1 plus F2. That's what's on your equation sheet. F1 plus F2. But it's the force of friction plus the force of the slide. That's an S. So force of friction is negative 20 newtons. Force of our slide is 80 newtons. Add them together and we got 60 newtons. Okay? But that's actually not what the question's asking for. It's asking for acceleration. So now I go back to my equation sheet, and acceleration equals force divided by mass. So 60 newtons divided by 80 kilograms. And I got 0.75 meters per second squared. So that is the answer. So notice though, this is pretty common, especially dealing with friction, is you're going to have to solve for a total of the forces to see what the result is, and then plug it into another equation of some kind. Okay? So let's do the next one. A 1,200 kilogram car, its mass, is traveling at 30 meters per second. That's a velocity. When the brakes apply a frictional force of 3,600 newtons, force of friction, what is the acceleration? Question mark. So I draw my picture. I got a car, mass of 1,200 kilograms. 30 meters per second is my velocity. And my force of friction is negative 3,600 newtons. Do my KUF. Oh, what am I looking for? I'm looking for acceleration. I didn't put that on there. KUF, knowns, mass is 1,200 kilograms. Velocity, this isn't a starting velocity, so I put V0 equals 30 meters per second, and my force of friction is negative 3,600 newtons. What am I looking for? Acceleration. We've got all the forces we need to know about, so we can just simply use force divided by mass. So acceleration equals 3,600 divided by negative 3,600 divided by 1,200, and that's equal to 3, but it's a negative 3 meters per second squared, which that checks because she's braking, she's slowing down, so the car's acceleration is, her velocity is changing in a negative direction, so it should be a negative number. So my acceleration equals negative 3 meters per second squared. That's part A, but look at part B. How long will it take the car to stop? So stopping means that's a V0, right? Or that's a V, that's actually the second. We're already moving. I'm going to draw this picture again. We're already moving at 30 meters per second, right? But the car is going to stop, which means the car has a V1 equal to 0 meters per second. So V1 equals 0. Anyway, you circle that one, V1. Sorry, I added extra stuff there. Okay? But how long? So our question is how long, and that's a time. Okay, so let's go to our problem. So how long, time, stop is V1. So I've redrawn the picture. I've got my car here. It's going 30 meters per second. It's accelerating at negative 3 meters per second squared. That's from the previous problem. Okay, and what's our time? So acceleration over here, I fill in my chart. And now I look for an equation. Now, correct me if I'm wrong, but I do not see an equation on your equation sheet that directly corresponds to this problem. So what you have to do is A equals V1 minus V0 over the change in time, which is T1 minus T0. So negative 3 equals, what's V1 is 0 minus negative 30. Sorry, that's positive 30. Minus 30 divided by T1, which we don't know, minus T2, or T0 the second time, starting time, I'm sorry, which is 0, right? We started at 0 seconds, right? And I'm going to continue my work on another sheet of paper, okay? So let me rewrite this. So we've got A equals V1 minus V0, T1 minus T0 equals negative 3. That's acceleration. V1 is 0, V0 is 30 over T1 minus 0. Do our math. Negative 3 equals negative 30 over T1. Multiply both sides times T1. Those cancel. And then divide by negative 3 on both sides. Negative 3 divided by negative 3 cancels to 1. And now we've got T1 equals negative 30 divided by negative 3. Negative divided by negative is a positive. So 30 divided by 3 equals 10. Takes her 10 seconds to stop. Okay? And if you have a simpler equation, you should still get the same answer. Okay, so let's recap real quick. Friction. It could be quite complicated, but to keep it simple, what I really need you to remember is friction is a resistance, is opposite the motion of an object, and it's based on, it happens at the surface. The force of the push has to be greater than the force of friction for it to move in that direction. But as we saw with the car tire, the force of friction is actually what makes the car move. Okay, because we can use, as long as there's a positive force, it's going to accelerate in whatever direction. The change in motion is going to happen in the direction of the winning, the bigger force. Okay? So, what I want you to do now is there will be an assignment in Google Classroom for you to practice some of this. Okay? All right. Thank you. Have a good day.